So now we have an example of two functions which are not inverses, namely x squared and the square root of x. Now you might think that they are inverses because if you plug one into the other, looks like you get x, right? Okay, you might think, okay, well, isn't this true? Well, it is true, but it's only true if x is positive. If x is negative, then you're trying to square something that's undefined in the real numbers. So this is equal to x only if x is greater than or equal to 0. And in fact, we can see that if we can do it the other way, what about the square root of x squared? Well, this is only going to be equal to x when x is greater than or equal to 0. Because, for example, if we take the square root of -1 squared, okay, that's the square root of 1, which is 1, which is not equal to -1. Okay, so this is not, so even though it, even though this is true, this is true for this is not true for all x in the domain of where it's supposed to be. Now we can fix this a little bit by defining the next example by defining this function, and we only define it. We restrict the domain of this function h to be when x is greater than or equal to 0 on the non-negative real numbers, and we just say it's undefined when x is negative. Now they're going to be inverses of each other, because now this will hold. This will hold for all x in the domain of h, and this holds for all x in the domain of g. So these are inverses for the same reason. Now we'll come back to this in a moment. But I want to go over some properties of inverse functions and how they relate, how the inverse of a function relates to the original function. So if f is a function and has an inverse, then we have, this is probably the most important part, f of a equals b if and only if f inverse of b equals a. What this means is if a is an input and b is the output under f, then b is the input and a is the output under f inverse. In other words, the roles of a and b are reversed. And the reason why that's true is if we take this equation and we apply f inverse of both sides, okay, and then the f inverse and the f cancel out, and we get a equals f inverse of b. And then similarly, we can apply f to both sides, and we'll get back here again. So these are, so basically, the inverse, the inputs and outputs are reversed. And as a result, we have the fact that if AB is on the graph of f, then the point BA is on the graph of f inverse, because this and this mean the same thing, and this mean the same thing. And we'll see that as a result of that, I'll skip to number 4. The graphs of f and f inverse are symmetric to the line y equals x. That means, in other words, if you take a point and switch interchange the coordinates, you get a point that's directly across this line y equals x. Okay, so these graphs are, the graph of f and the f inverse are symmetric. Now that's not to say that this graph always has to be on one side of this dotted line. It could cross, but then this corresponding graph over here has to cross as well. So the graphs are symmetric with respect to this line y equals x. We also see that the number 3, the domain of f inverse has to be the range of f. All this is saying is that we're saying the inputs of f inverse equal the outputs of f, and the outputs of f inverse equal the inputs of f. Okay, so inputs, outputs, their roles are reversed. Now, another important, not every function, as we saw, has an inverse, as we saw in example 4 just now. And it turns out the only functions that have inverses are the functions that are one-to-one. And the reason for that is that if f is not one-to-one, let's say if we have f of 1 equals f of 2, so say, so if f is not one-to-one, maybe this happens. And then if f has an inverse, we apply f inverse to this. And then all of a sudden we get 1 equals 2, which is not true. Okay? And we're going to have this, we're going to run into this problem any time we have an output with two different inputs. So you have to have, a function has to be one-to-one for it to have an inverse. And it turns out that if a function is one-to-one, it always has an inverse. You can construct it. So, and just to go back up here, if we looked at the graph of x squared, we know what the graph looks like. It's this parabola, right? And that clearly does not pass the horizontal line test, so this is not one-to-one. Okay, so there's no inverse possible. But if we were to graph h, if we graph this function y equals h of x, then we just get this right half of this parabola. And in fact, if we were to graph this function along with the square root of x, we see that they are symmetric with respect to this line. Okay, line y equals x. Okay, which, as we said, that's what should happen.